Мгм. Так. Так, ну вроде мы записываемся. Слушайте, по поводу организации я сегодня вам предлагаю следующее. Смотрите, позаниматься без перерыва до половины седьмого, ну или там, скажем, 18:20, что-то такое. И потом я тоже хотел вас пригласить вот на семинар по теории доказательств, собственно, совершенно по нашему предмету, который будет вести Лев Беклемишев. Это человек, академик Российской академии наук, который вот в этой науке, наверное, то есть точно самый, так сказать, значительный и продвинутый человек вот в нашей стране, но и очень признанный также международно. Давайте вот сейчас мы начнем собственно, продолжим то, чем мы занимались в прошлый раз, и потом, может быть, вот после 18 часов я вам чуть-чуть скажу там пару слов, то, о чем вот будет рассказывать Лев, чтобы вам было понятнее, к чему там он будет говорить. Но там, как видите, тема, речь пойдет о работе австрийского логика Георга Крайзеля, который недавно умер в очень уже солидном возрасте, про фундаментальные проблемы, связанные как раз с соотношением формальных и неформальных доказательств. И, собственно, именно то, что мы обсуждаем сегодня на курсе. Так что я надеюсь, это будет всем очень полезно, как дополнение к тем лекциям, занятиям, упражнениям, которые вот я с вами здесь делаю. Вот. Okay, so let me switch to English. Now I share again my screen. Can you see the exercises? It's called exercises.
Yes.
Okay, let's go through maybe briefly through these exercises. I think I recommended these exercises in a message. Yeah, no, the first exercise is a problem which is similar to problem that, or rather puzzle, that we solved last week. And it took us, I think, about hour and a half just before the break. And I think it was quite reasonable and good. But to do this once again, I don't think it would be a good idea. So I don't know if anybody can just give the solution who already worked it out, or if not, we just skip it. So
I tried to solve it.
Okay, then.
So my solution is that mother is the murderer, son is the victim, daughter is the youngest, and she's the witness, and father is accessory or something like that.
Mm-hmm. But Marie, yeah, good, Marie. But could you? I understand that we should first learn the problem, read the problem. But can you just present the whole thing? Just give us the problem, and then solution, and then a proof of your solution. Of course, in a sense, the key point for our course is a proof, right? Yeah, so please just first explain the problem. Second, just restate your solution, and then prove it. Yeah, that's a big program, but just at least as mathematicians say, sketch of the proof, right? Maybe without a lot of details, but please, yeah.
Okay, so we have a family of 4 people.
Mm-hmm.
So there is father, mother, son, and daughter. And one of the members of this family killed another member. And one of the members witnessed the murder and another member was accessory. And we have to figure out who is the murderer. And we know some facts. And should I read all the number one, the accessory and the witness were of opposite sex? Should I do that?
Sorry, I think everybody can just read them. Okay, so yeah,
Okay.
we have these facts from 1 to 6, so please read them. I think you can just use them during your proof, and that's how we'll take them into consideration.
Yeah, okay.
Yeah.
So we know that the father was the oldest member, and I tried to figure out who was the youngest member. Obviously, mother cannot be the youngest member, so it's either the son or the daughter. And then I kind of методом выбора. If we speak
Method
Russian,
of choice.
yes, I tried. So I decided that son was the youngest, and therefore the victim was.
I'm sorry. What do you mean by method выбора? So it's a hypothesis, right? So you just
Yes.
consider cases. If I understand.
I considered several cases, and then I applied this kind of circumstances to these cases and saw if it fits or not. So with son, the victim was either the mother or the daughter, but both of the cases didn't work out. So it means that the daughter was the youngest. And if the daughter is the youngest.
I'm sorry, and what did not work out?
The cases, it's difficult to explain. So if father is the oldest, then one of the children is the youngest. And let's say that son is the youngest.
Right.
And because we have the oldest member and the witness we have the third one, the youngest member and the victim were of opposite sex. So if the son is the youngest, then the victim is either the mother or the daughter. And then we kind of have cases where son is the youngest and mother is the victim, and then son is the youngest and daughter is the victim. And none of this worked out. So I decided to try daughter as the youngest member.
But what do you mean none of that worked out? So it should...
There were cases that both of these cases didn't match up all of the circumstances.
But which exactly circumstance, say the subcase one, that mother is a victim, doesn't fit? Okay,
if mother is the victim, then son is the mother is the victim, son is the accessory, and daughter is the witness, and father is the murderer. And I didn't. Okay, the murderer was not. So if mother is the victim, then father must be the murderer, and therefore son was either the accessory or the witness. And
accessory was
was older than the victim. That doesn't match. And if daughter is the victim, then then I think also the fourth one doesn't match. Or
and why? Daughter is the victim, accessory.
Daughter is the victim, mother is the witness, son is the accessory, and father is the murderer. So it doesn't match up because the son is the youngest member of the family, and he's also accessory, but accessory was older
Okay.
than
Yeah. Thank you.
the victim.
Right.
So that's
right. Mm-hmm.
and the kind of like the second group is cases where daughter is the youngest member, and let's say that son is the victim. So son is the victim, daughter is the youngest member, and she's also the witness. Let's say that mother is accessory and father is a murderer. It also doesn't match all of the circumstances because
all of conditions, those things
yes,
are conditions rather than circumstances. Okay.
Yes, conditions, because
yeah, you can also say circumstances, probably, right.
Because
yeah.
in this
logic
case,
you would rather talk about conditions, but in real life you might talk about circumstances. Okay.
So in this case, daughter is the witness and mother is the accessory, but it cannot be possible because accessory and the witness were of opposite sex.
Right.
So the next case is when son is the victim, daughter is the witness, father is the accessory, and mother is the murderer. And in this case, everything kind of like matches. All the conditions are true to the case. So the accessory being father and the witness being daughter are of opposite sexes. The oldest member and the witness were of opposite sexes, so father and the witness, the daughter, of opposite sexes. The youngest member and the victim were of opposite sexes. The youngest member is the daughter and the victim is the son, so they're of opposite sexes. The accessory was older than the victim. Father is the accessory and he was older than his son. The father was the oldest member. That is true. And the murderer was not the youngest member. The murderer was mother. She was not the youngest. So that's it.
Yeah. Thank you very much. Bravo. Right. You spent the time. But just general remark that you see in cases like this, of course, it's actually more than one statement. Or of course, you can kind of pack it into one. But when we're talking about the murderer, right, we kind of assume that the murderer is unique. But actually, we don't really need to assume that, right? Because it's something that actually follows from those conditions. And but then, of course, it's equally important to prove that someone is not a murderer, right? So we prove this negative fact or negative proposition. And that's how you did when you came to contradiction, right? Then you made this hypothesis and then derived a contradiction and concluded that since you derive a contradiction, then it's not the case. And this is very fundamental. This is going to be one of our rules of natural deductions, among other things, right? That we derive negation, we derive falsity from contradiction. That's very important, and so the whole solution actually comprises quite a few kind of lines, right? So roughly speaking, we should take everyone and prove or disprove that he or she is a murderer, right? And if we do all that with all these 4 people, so we actually have these 4 parts in this proof, right? And where each part concerns each person involved, right? And basically we either disprove that that person is a murderer or prove it. And then it actually happens that it's disprovable in all cases but one, right? That's not just a more systematic way of and more abstract of what you just presented. Right. Thank you very much. And of course, practically speaking too, right? It's important to accuse a person, but maybe even more important is clear up somehow to prove that someone is not guilty. That's practically speaking is probably even more important than convict the murderer, right? Okay, that's probably there are some questions from the audience on this exercise. No, if not, let's move on. And actually, then there is a couple of exercises which are logically speaking rather simple. There is nothing, no tricky things involved, unlike this first exercise, right? But I think they're important because, you know, they this kind of exercises that allow us to make a link, to bridge, if you like, natural language with artificial language, right? Or something expressed with usual English, translated into something expressed with logical formula. And that's, of course, very important translation. I should say that it's actually much more subtle issue than it may first appear, I would say, right? Because, of course, say in cases like this one, we already use some certain fixed logical scheme, right, for interpreting natural language. And of course, here there are many options, right? That's what we study is rather basic. It's not very subtle case, but still it could be different versions actually how people can do this. No, still we need to learn at least one to talk about others, right? However, I think that's something to be kept in mind, right? That this translation is not whatever automatic, is not canonical, as mathematician would say, right? And it's and that's exactly a part of no, logic is a big thing, I told you, but a part of logic which deals with natural language, and it somehow intersected, if you like, with what is called philosophy of language or formal philosophy of language or formal linguistics also, right? It's provide that kind of translation. Of course, your logical scheme should somehow correspond in a sense what we are doing in natural language. You cannot just translate natural language in anything. On the other hand, it provides certain standard, right? Certain, you know, formal restriction, and that's of course debatable, right? What it can be, what it probably should be, etc., etc. Right? But let's just look a little bit more precisely how it works. Right? So what they propose us to do in the second exercise is just, you see here this passage from natural language to mathematical language just goes via kind of abbreviation, via acronym. They call it mnemonic. So we just write F for father, M for mother, D for daughter, son, mu, mu for murderer, and V for victim, etc. And we can define propositional variables. Yeah. No, actually, what here they propose, because to do that more, how to say, more precisely, if you like, we would actually need first order logic. It's our next chapter, actually, yeah, because we are still doing propositional logic. And in propositional logic, we simply do not distinguish between, say, individual, like father, right, and a property, like being accessory, because accessory here is actually a property rather than individual, right? It's even in our setup, we have just exactly one accessory, one oldest person, one youngest person, etc. However, you see these things are rather properties, to be youngest, to be oldest, to be accessory in a murder, or and things like that. Why some other, they are like proper names. Yeah, no, being a father, you may say, it's a property, right? It's not a name. However, here would be kind of reasonable, right, to say that father, mother, daughter, and son are just proper names. You can call them, I don't know, John, Mary, whatever, right? However, being murderer, being victim, being witness, blah, blah, those are property. But I say it again, to distinguish, to make this distinction between proper name and name of property, on a formal level, we need actually more elaborated logical apparatus, logical tools, but actually we are going to study them. So it's not beyond other course, but not yet, okay? But here you see they just want to, to form propositions like FM, father is the murderer. So that's FM stands for father is a murderer, daughter is a victim, and so on. So it's just a, kind of mnemonic way to go around to mimic first order logic, if you like. Okay. However, anyway, let's accept that's what they propose us to do. But then let's see what happens. So they write this long formula, and I think that our task is translated this formula back into words, right? So what we are doing now, it's not translating natural language into formulas, but rather to make, that's what they did for us, the authors of this textbook. But now we are asked to make a backward translation, right? So there is this formula, and they want us to consider it first of all, and just to read it, what is written there. So may I probably ask someone, but maybe not Maria, but someone else, to read this formula, this long formula in a natural language. And then you see, of course, that then you can see the usefulness of formulas, if you like, right? Because such a not very complicated, but still rather complicated, you see have about 1, 2, 3, 4, 5, 6, 7 logical connectives and quite a few pairs of brackets, and then it's not immediate to express all this in natural language, right? Because our natural language, say if have something short like that, I think we would not problem with natural language, but a longer formula becomes less readable in natural language, of course, but still, let's try. Yeah, who would volunteer?
I can try.
Yes, please.
Okay, so if father is an accessory or son is an accessory, then mother is a witness or daughter is a witness. And if mother is an accessory or daughter is an accessory, then father is a witness or son is a witness.
Yeah, I think it's actually in that case. I think in linguistics they call it parsing. Do you know this word? Parsing, like PARS, like dollar, INJ. Parsing. I think it's a term used by linguists, and it's refers to that kind of analysis. You see, so you have a phrase. No, rather parsing is, of course, it refers to translation into formula, right. But still, the idea is that you have this, say, piece of text, and then you distinguish some logical relations where there is subjects and where there is predicates, things like this. Somehow you understand the structure of this linguistic expression. So that's called parsing, technically. So a phrase like this is parsed, you see, smoothly. Yeah, maybe it's just taken for example. Okay. Yeah. No, okay, that's probably boring. They ask us to do similar things with all other cases, but okay, let's keep it. Otherwise, we don't have time for more interesting things. Yeah. Exercise number 3 now. Consider the following 3 hypotheses. Ellen likes kangaroos, and either Betty likes frogs or Carl likes hamsters. I forgot who are hamsters.
Хомячки.
Хомячки. Спасибо. If Betty likes frogs, then Ellen doesn't like kangaroos. If Carl likes hamsters, then Betty likes frogs. Write a clear argument to show that these 3 hypotheses are contradictory. Okay, let's do this. Okay, so I think what we should do is first formalize it. It's that kind of way. No, actually, we don't really need a special letter for Carls or beta or frogs. I think we can simply formalize the this kind of elementary sentences. Like, you see, Ellen likes kangaroos, Betty likes frogs, Carl likes hamsters, and we can call them P, Q, R or something like that, and then introduce logical relations. So yeah, so let's do this. Or probably someone already has done that as a homework. No, if not, let's just do it now.
Well, I've tried to write the statements in a formal way. So the first one probably let's say that Alan likes kangaroos. We can write it as AK, and then Betty likes frogs. It's BF, and Carl likes hamsters.
Oh, I can actually write here.
Oh,
okay. Yeah. No, I don't know. Yeah. How you would like to call it? Which letter?
I just combined the first letter of the Alan's name and K. Then.
Yeah. Okay, we can do this. AK. Okay. And that's, I suppose, going to be BF, right?
Yes.
Okay. BF, and that's CH. Okay. Right?
Mm-hmm. Yes, yeah.
Okay.
And then we need to write the symbol of conjunction between AK and BF.
Now,
to say and.
But actually now it's matter of parsing. Это как вот казнить нельзя помиловать, да? Где Let's be accurate. Ellen likes kangaroos and okay. No, at least my understanding of English grammar, we may probably discuss, is this, that then we have and, right? And then we have the injunction.
Yes.
Yeah, I think it's like this. And yeah, and you see, in natural language is not always obvious what should be done. Okay. OCH. Okay, we have this.
And then the second one, BF. Then.
That implies, right? If then.
Yes.
This implies.
Implies not AK. I guess it's. I'm
right.
not sure.
All right. Yeah, I think that's correct. Exactly.
And the third one, CH, implies BF.
CH implies, right, BF. And now they actually want us to prove that they are contradictory. We may also say not compatible or not consistent. Ну, давайте я вам немножко объясню вот в смысле русско-английского перевода, потому что это не очевидно. По-русски говорят, что, ну, допустим, набор высказываний не противоречив, да? Или когда говорят непротиворечивость, значит, не... Это, кстати, калька с немецкого, я забыл, как. Widerspruchlos, это значит непротиворечивый по-немецки. Потому что у нас это вся логическая, ну, у нас в смысле в России логическая терминология где-то вот в конце XIX века формировалась под влиянием в основном немецких всяких учебников. Непротиворечив, ну, вы или вость, вость, давайте напишу, да? Да, значит, по-английски, вот кто, может, знает, как перевести слово непротиворечивость или непротиворечивый? Но если не знаете, лучше не гадайте, потому что это, ну, как бы терминологическая такая штука, и она, в общем, по-английски это называется consistent или consistency. Stand, ну или consistency, да, непротиворечивость. Вот, запомните вот это, ладно? А наоборот, противоречивость, ну это, наверное, проще. Знаете, как на английском, да? Как противоречие по-английски.
Contradiction?
Contradiction, да. Это как бы латинское на самом деле, да? Dictum, contradictum. Contradiction. Но важно, что вот это consistency, а не что-то другое. Видите, как-то с русским не очень. Да, ну по-английски, когда вот такой набор предложений, если мы на такой не очень формальной логике, можно сказать, что они тоже, ну также и по-русски, можно сказать, они совместимы, там, по-английски compatible, или несовместимы, not compatible. Ну, то есть это такие уже менее технические выражения, но которые значит одно и то же. Okay, that was just terminological remark. So we ask to prove that these three conditions actually are contradictory, right? So they are not consistent. Yeah, противоречивость еще называется inconsistency. Вот, давайте тоже это скажем. Не противоречивость consistency, а противоречивость будет inconsistency. Или Вместо того, что система противоречивая, contradictory, но это тоже такой менее формальный, а в более такой математической логике люди бы сказали inconsistent. Consistent. See. So we asked to prove that the three statements are not consistent, are inconsistent. Yeah, and since, of course, we can do that more formally and less formally. Let's probably try something less formal first, and then we'll see how it's formalized.
Well, I guess the contradiction is kind of obvious, because if we suppose that this sentence is true, we need all of its parts to be true, which is impossible.
Be accurate. All conjuncts, right? What is the left on conjunction, right of conjunction. However, we also have disjunction. So it depends what you call all parts. Right, so to be more precise, we have a conjunction of two conjunct, one of which is elementary. This is our AK, and the other is not elementary, right? It's itself a disjunction. So since it's conjunction, right? We both of conjunct, ну как-то конъюнкты, conjuncts, both of these should be true, right?
Yes, and the part with the disjunction, it can be true even if one of its parts is false. Right? But
no, it is true. Say it again.
Well, I'm talking about disjunction now.
Disjunction, it is true, just in case. What? Because you said something.
I'm kind of confused, sorry. Even if one of the parts is false.
Yeah, but again, you see, that's linguistically something not very clear. I would say it is true if at least one of conjuncts is true, right? At least one. But that also includes the case when one of the other conjuncts is false. Okay? But then you say it's true even if, and that's kind of emphasis on even. However, what that emphasis implies logically is less clear. So yeah. Okay, go ahead.
But because of the third statement that if Carl likes hamsters and Betty likes frogs, both parts of the disjunction, they should be true.
Yeah.
Well, because if we say that Carl likes hamsters is true, then automatically Betty likes frogs, and that's also true. But then we have statements that if Betty likes frogs, then Alan doesn't like kangaroos. And if we just came to the conclusion that Betty do like frogs, then automatically Alan can't like kangaroos, and the whole sentence is impossible.
Okay. I see. So you really derived contradiction. However, I'm not sure that you really systematically explored all hypotheses, you see? So again, we have cases here and cases because of the disjunction, right? So AK is true in all cases if the whole thing is true, because that's conjunction, right? But then we have cases, and actually we have what? We have 3 different cases. No, if we just look at first formula without considering the second and the third, right? So it could be that BF is true and CH false. It could be that CH is false and BF is true, and it could be that both are true, right? So we have actually 3 cases, and we should now show that none of these 3 cases is possible in view of the second and the third condition, right? And yeah, and if I followed you correctly, I probably cannot see that you really explored all of these 3 cases, all of them. So we should rule out these 3 cases one after another, right? But they should be 3. Okay. So I would propose to reason, let's BF is true and say CH false. Yeah, but if BF is true, we rule out that case because AK is true and BF implies non-AK. So BF implies that AK is false, and that doesn't go through. So we already may rule out case where BF is true, and also case actually where BF is true and CH is true. So BF cannot be true, right? Okay, so so there is one case remaining where BF is false, but CH is true. Okay. However, in view of the third condition, CH implies BF. So, and since we already rule out this possibility that BF is true, this third case is also ruled out. Yeah. Did everybody follow the? Yeah. Yeah. Okay. Yeah. That's. I think that's it. However, just maybe a couple of short commentaries. No, first comment is that you see it's actually again kind of usefulness of formal logic, if you like, right? And just symbolic logic, because it's kind of tiresome to keep in one's memory all this reasoning. It becomes kind of you see it's easy to lose the track, right? And when you have these formulas, it's kind of easier to follow what's going on. That's one thing. And but kind of deeper remark is that this say informal reasoning, no, which is close to be formal, but still was in language in that sense informal, it was semantic. It was not syntactic. Why? Because we talked about truth and false. Actually, we can give an argument here without applying, without referring to truth and false, right? It's actually sufficient to show that we may derive a formal contradiction. That means that we may derive situation where we have certain proposition and its negation, like AK and non-AK, right? And so we may, if you like, forget about truth and false. Of course, that's the meaning of all that, being true and being false, of course, right? But at least this is a theoretical possibility, and you'll see it's also a useful possibility in a sense. Just analyze this contradiction, not in terms of truth and false, but in terms of just formal contradiction. And formal contradiction is then you saying something and you negate the same thing, you see? And that's formal contradiction, right? It's if you bring in semantics, when we say, okay, what's going on? You say first that say certain proposition is true, but then you also derive negation of the same proposition, which means that the same proposition is also false. And that's contradiction. It cannot be both true and false. Okay. Yeah, but that's again semantic. But without going to the semantic way, okay, we can simply say that's okay. It's just AK and not NK, and that's already contradiction, without even referring to truth being true or being false. Okay. Now, if there are any questions, please don't hesitate to interrupt and ask me whatever. Okay. I'm trying to wait. Oh, sure. Sorry. Yeah. That's it for exercises. Now let me. The only thing I don't know now how to clean my stuff. Probably I do. As in the class, I just do with. Yeah. That's way. Okay. Yeah, so let's going back to our sheep, I don't know. Знаете, по-русски говорят, вернемся к нашим баранам. Это как rentrons à nos moutons по-французски. Ну, по-английски так, как кажется, не говорят. Но давайте все-таки мы к ним вернемся. Опа. Not sorry. I think we stopped. Right, we stopped here. Right, we stopped here. So I recall what we are doing. We are studying a special system of formal logic, which belongs to the type of formal logic called propositional logic. I already explained last time what it means, even recall a bit today. So it's actually core logic, if you like, and later we are going to extend it to so-called propositional logic. Okay, and actually what we are studying now is what is called deductive system. Is a formal system, symbolic calculus, right, where variables represent propositions, okay, and where we have certain special symbols that we call propositional connectives, like conjunction, disjunction, implication, and negation. And we have certain rules. So what is specific for this approach, and that's why we are talking about proof theory rather than some other department of logic, is that our basic object is a rule, right? And probably are recalled, and rules are needed to infer some new proposition from some given propositions, and those given propositions are called premises. Okay, remember, which more specifically can be described with a certain epistemic load as axioms or hypotheses or simply assumptions. All these words, axioms, hypothesis, assumptions, they're epistemic. Epistemic means related to knowledge somehow. Okay, so they just describe different status, different epistemic status of premises. So axiom is supposed to be, at least classically, supposed to be something self-obvious, something really known without proof. Some people would say, okay, again, here there is a lot of different philosophies, how people actually think about axioms, but general idea is that is something very basic, obvious, something we start from. Yes, hypothesis is a different, right? It's just that we make some statements, say, for the sake of argument. Знаете это выражение по-английски? Ради аргумента, for the sake of argument. So, no, it's like was what Maria presented us, right? We say, let's assume that, say, son was the murderer, and then this and these things follow, or let's assume that father was the murderer. And so if you assume this is a hypothesis, right? You really don't know if your hypothesis is true or false. However, you just use it in your reasoning, right? That's hypothesis. And the assumption, no, it's a bit like hypothesis, I would say, except it's actually broader, maybe. At least this is my linguistic and, say, logical intuition about assumption. So you may assume something as a, or some proposition as a hypothesis, or you may assume something, say, as a convention, for example, right, or some agreement. So it gives kind of epistemic freedom, if you like, to okay. And if you say premise, is just formal. So again, it could be axioms, it can be known, unknown, whatever. It simply says it's above the bar, where the bar means the inference, okay? And as I told you, the kind of basic scheme of inference in that calculus that we're studying, which has a name of natural deduction, and natural refers to the argument that it's really fits quite well, say, how people really reason with natural language, maybe better, arguably better than some other systems of formal logic, right? So here we have multiple premises above the bar, okay, and a single conclusion below the bar. Yeah, and actually, can you see now this modus ponens? Is it visible for you?
Yes, it's visible.
Okay. I just asked from time to time. Okay. And here we started. So what we are going, we study these rules, which together constitutes what is called natural deduction, or system of natural deduction, or calculus of natural deduction, right? And we just go rule by rule, and at the end, if I have time today, or maybe or maybe next week, I'll give you the whole system. So basically, it's a system of rules, but we just explore them so far one by one. And so we started with so-called modus ponens, which in the context of natural deduction has also this more specific name of implication elimination, which means that above the bar you have elimination, but you have it no longer below the bar. So it eliminates implication in that sense, right? And okay, we discussed modus ponens, and even I mentioned the modus tollens, yeah, which in this system is considered to be a derived rule. So we may derive this modus tollens by it's going to be an exercise, okay? So just by combining some basic rules which we somehow assume to be basic. Okay, so it's yeah. So we started with modus ponens, and then we considered the corresponding introduction rule. So that's again something specific for system of natural deduction, where rules of two sorts, introduction and elimination. So this rule introduces implication. If modus ponens, it eliminates implication in the sense that I just explained. That rule introduces implication. And that works as follows. We just assume A as a hypothesis, and that's actually essential that it's not an axiom or something, right? Then we derive via some number of steps, right? You see, in that sense, it's kind of schematic rule. We need to use dots to describe it. And dots actually stand for some combination of rules which we are going to study later. So rules of natural deduction. But the idea is that somehow if we infer B from A, we actually infer implication. A implies B, even without actually saying that A is true. That's the trick. And this is expressed by a operation, if you like, which called a canceling or discharging of hypothesis. You see, so you start with A as hypothesis here, right? It could be also known thing, A, but not necessarily so. It could be just like, let's assume father was a murderer, and then we reason. And if we, using this hypothesis, we derive certain other B, say whatever, mother is a victim, or what have you, then we may actually introduce implication, and that implication is true whether or not A is true, was true. No, intuitively it's clear, right? It's just that B is implied by A, and that does mean that A is true, right? It simply means that A implies B, okay? And that is what is called discharging hypothesis. So we are no longer, so we made this reasoning from A to B, but then if we introduce this implication, that means that the further reasoning, whether we may use this implication, no longer depends on that hypothesis. You see, we don't need any longer after that step to say that our reasoning is conditioned by this hypothesis. That conclusion will be only true if A is true. No. After we have this implication, is just that's, by the way, interesting. You see, in this calculus, we may derive or infer certain true propositions, even if we are not going any true propositions in the beginning. You see, it's not that we derive B from A as a theorem from an axiom. It's not like this, right? It's simply we take hypothesis, we do something, and then we derive implication. Implication, which you may say it's a theorem, but or whatever, how you want to. That's, of course, another epistemic word, like theorem, axiom. But actually, it's derivable with no assumption, given, of course, that this derivation from A to B really is valid. And here we cannot say it's valid or not valid because we have these dots to be replaced by something more concrete. Okay, that's so far about these two: introduction, elimination, and introduction, implication, implication, elimination, and implication, introduction. Okay, the two complementary rules. And then I think at the end of our class last week, we also considered conjunction, where we also have this double, two types of rules of elimination and of introduction. And here we actually started with introduction. I think it's more natural order in this sense, first talk about introduction and then elimination, rather than the other way around. I think it's only for historical reason, because modus ponens is so traditional and in a sense so fundamental in logic and the history of logic that they started in that case with this rule, which is a rule of elimination, right? In conjunction, we follow more natural order, if you like. So first rule is how conjunction is introduced, and that simply rule says if we have these two assumptions or these two premises as A and B, then we may derive conjunction of A and B. Right? But again, it looks kind of very elementary, very simple, but it's still a step. We have two prepositions, namely A and B above the bar, right? And we have single preposition A conjunction B below the bar. So that's, if you try to spell it in language, it looks like you don't do anything, right? It just, you say A and B above the bar and A and B below the bar. But the thing is that and is not the same and, right? Because below the bar we have and as logical connective, and above the bar we have a and as a, no, if you like, logician would say metalogical. But, so it's like Peter and Mary, or Andrei and Marina, or something, right? It just so two objects, two variables. So there is still something important that's going on here. Yeah, so that's a introduction rule for conjunction. And then we have actually not one, but two elimination rules for conjunction. And there are two because we have two conjuncts. So from conjunction A and B, we may derive A, and we also may derive B. And that gives us a two, like left elimination. You see here, little L, little R, that means left and right elimination rules for conjunction. Right. I think, yeah, if you still have some questions, please ask. But I think it's where we stopped last week. No, okay. If not, let's go on. And now we are going to introduce another rules which refer to negation. So first rule is introduction, again, negation introduction. You see, and actually that's pattern of reasoning again was already today in our exercise. So it also works in a sense similar to introducing implication, and similarity is that we may also discharge hypothesis here, right? So example of this reasoning was, say, referring to this puzzle of today that Maria presented to us, right? We say, let's assume father is the killer. Frankly, I forgot what was the right answer. Who was really the killer? Maria, who was the killer there?
It was mother.
Mother. Okay. 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 So right. So let's we say A is hypothesis the father is the killer. Okay, and that's how Maria reasoned, and that's how one should reason indeed to solve this kind of puzzle, right? We assume that father is a killer and call this proposition A, and then we reason using, of course, our facts, our conditions should be given something, and then come to contradiction, right? He cannot be the killer. So basically we derive contradiction, and formal contradiction is just means that we derive not A, right? So we start with A, we derive not A, and that thing A, not A, we call contradiction. No, they somehow skipped it. Let me probably write it again. Yeah, because we also have introduction rule for contradiction, and that looks like this. No, we are going to see it later, but probably I just write it already now. So we have, say, A, it's one premise. Another premise will be not A. Okay, so we have these two premises, A, not A, and this is what we are going to call contradiction. But it may be not immediate, right? It may go through certain steps, certain conditions, as in this example. So we start with A as hypothesis, and finally, somewhere here, we should have not A in these dots. And then we use that would be introduction of contradiction. And then we derive contradiction, but important that at that point, when we derive contradiction, we actually introduce negation. So we conclude that not A, and again, we discharge this hypothesis. This is important, right? So, so finally, we just have not A. We derived not A as a definite, judgment, if you like, right? Which does no longer depend on our hypothesis. So if we derived contradiction from a hypothesis, that means that we refuted it, if you like, right? And so logically speaking, that means that we proved it negation. That's how it works. Okay. And oh, sorry. Right. Yeah. And actually, they have it here. Yeah. Somehow, what I already showed you earlier. This what is written, right? They just introduced it a little earlier. So this is yeah. And yeah, the thing is that yeah, I called it. Yeah, I called it introduction of contradiction, but that's actually wrong, right? Because contradiction is actually an object, it's kind of constant name. We consider this, you remember we called it falsum. And the idea is that in our, say, universe of propositions, we have these propositional variables like A, B, C, whatever, which refer to propositions, which may be usually true or false. However, we have also kind of special names, two proper names of proposition, one of which is just true, or we may say always true, so it's not a variable, it's a proper name, and the other is always false, and we call it falsum, and this is the thing, right? But since we have negation here and no longer have it under the bar, yeah, that's actually, we can call and should call elimination of negation, and consider it on a pair with introduction. So what's going on? Yeah, that's help. So you see, here we introduce again negation via that sort of reasoning, and here we eliminate negation. Okay, and again, this introduction and and elimination actually refers to propositional connectives. So we should talk about introducing this falsum because it's not a connective, right? It's not something that we introduce or eliminate. It's something given from the outset. Okay. Yeah, they also say, I think I already mentioned that, the elimination rule, this one, no, sorry. So they still talk about, yeah, because we also have this rule. Consider that is the next. So now we already have two, right? Introduction of negation and elimination of negation that way. But now we also have elimination of contradiction. And let's consider this. All right. Yeah, this one. So here we have a contradiction above the bar and some A, actually whatever A we want under the bar. And that's, we may also say it eliminates contradiction. Here actually is the same rule which introduces, so I still would call it introduction. Introduction, this one, introduction of contradiction. I think it's right to call it that way. But the same very rule we may also describe as elimination of negation. No, okay, whatever. We should ask Lev Beklemyshev what is the orthodox view on this deep question. Yeah, but that's important. You see what they say, the elimination rule, elimination for contradiction, also has the fancy Latin name ex falso, I think it should be falsio, sequitur quod libet, which means anything you vote follows from falsity. And well, we already discussed this, right? That's no, in a sense, this rule simply not follows, but somehow I would say fits the whole system of logic. No, remember, let's talk semantically speaking, right? Remember the truth table for it's truth table for implication. So it's true, 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 false, and false, true, and false, false, right? And you remember that here we have true, and here we have false, and here we have true and true, right? That was a table, truth table for implication. But then also remember modus ponens, which is A implies B, it entails B, okay? It's modus ponens, modus ponens. And so now you see, what we say is if we have something which is false, A, yeah, if we have A false, then implication is always true. That's the thing. Yeah, and that's roughly that means the following, that at place of B, we can just substitute whatever we want. You see, so in that sense, so we get a I'm just thinking how to motivate that better. No, probably let me also add not A here as another assumption. So I have not A, and A follows B. And here I have a contradiction, obviously sitting there, right? And since I have this contradiction, I can take this A and refer B, right? And that's actually works for whatever B I want to choose, right? And that basically means that you see, if I have a contradiction, I may infer whatever I want. Yeah. No, actually, there are so-called called para-consistent logics. Para-consistent logic. So those are systems of logic where this rule does not fully apply. You see, so people try to, how say, to tolerate contradiction. No, by saying that, say, in real life it happens that something is true, then no, it depends, right, how you think about contradictions. Because this idea that contradiction just implies everything, it may seem counterintuitive, or maybe also seen as intuitive. Basically, it is the reason why contradiction is something wrong about it, right? So if you say, you know, it's like in Orwell, if you're saying that war and peace and war and things like that, then you just, you can kind of prove, in quotation marks, anything, just anything. And that looks like, you know, what really happens also in life. No, however, some people say that, okay, contradiction should be tolerated, but then you should really invent a different system of logic, which are called paraconsistent logic. And there are some logicians, maybe I give you even name, I think Graham Priest, he's kind of guru of paraconsistent logics, his name, from City University of New York. Graham Priest. Yeah, so there is certain people, but standard logic say just accepts this rule. Yeah. Okay. Now, what probably I want to emphasize, you see, it's not, logic is not kind of thing that you can accept or not accept a single rule. You see, you may try to, if you don't like somehow system of logic, some say classical logic, whatever, I don't know, you may dislike it. You may have some motivations, right, to develop different system of logic. No, in particular, by saying that contradiction is a good thing. By the way, Russian philosophers who begin 20th century were very, how say, fond of contradictions, like Alexei Losev, or, you know, they say those stupid Western formal logicians, that just don't understand how contradictions are deep and important and blah, blah, blah. Or, for example, German philosopher Hegel also developed, but the informal in that sense, right? Kind of philosophy and theory of contradiction, or actually something he also called logic, even it was not, certainly not mathematical logic, not formal logic. No, however, there were some important ideas, of course, there. And again, contradiction somehow played a key role in Hegel. So it was not just that contradiction makes everything trivial, makes, every proposition true. Right? So one may have some, say, good reasons to be not satisfied, say, by standard logic, but then to invent a new system of logic, you can just change one rule and just say, okay, I just don't, I don't like this rule, so I'm modifying it somehow, right? And then that will be my new logic. No, because logic is like a, I don't know, building or mechanism or spaceship or whatever you want, right? Where different parts and they fit together and so on, and you cannot just replace one thing and no, at least if this one thing is sufficiently important, you can just take it out and put something new, right? Because if you take it out, this whole construction breaks, and so you basically need to make another spaceship. That's how it works, you see. Right, that's just my comment to these rules. Yeah, but let's see what the authors, I think that they're still trying to motivate it somehow intuitively. Yeah, let's. For some reason, when I write something here, then I cannot any longer move my PDF. Okay. Sorry. And so what I should do is, okay, let's go and then go back. Hop, and now it moves. Okay. So what the author proposes, a motivation for this ex falso rule, is the following. For every natural number n, if n is prime and greater than 2, then n is odd. Does everybody understand this? Prime – это как простое. No, odd and even. Everybody knows what are odd and even numbers. Не знаю, все молчат, я не знаю. Все знают или все не знают, или кто-то знает, кто-то не знает.
I guess we know.
Okay. Yeah, so, ну давайте по-русски. Значит, если число простое и больше, чем 2, то оно нечетное, да, потому что если четное, значит, оно делится на 2, и уже оно не может быть простым. Ну, если оно само не 2, да, вот число 2 тоже простое. Okay, so we have the statement. Now, how we use it as an example, we would like to say that this is a true statement, but if it is true, then it is true of any particular number n. Taking n equals 2, we have the following statement. If 2 is prime and greater than 2, then 2 is odd. Ну, давайте я ну, видите, в чем трюк, еще раз. Давайте я по-русски прокомментирую. Они хотят как-то, вот авторы, мотивировать, почему из противоречий следует что угодно. Да? Вот, ну, дать какой-то пример, почему это как-то вот интуитивно, убедительно совпадает с тем, как мы обычно рассуждаем. Там. Другой вопрос, что это формально, вот если просто мы это выкинем, эту штуку, да, то у нас, ну, как я вот вам пытался объяснить, просто вся логика это развалится. Но это, можно сказать, тем хуже для вашей логики. А это вот тут попытка, ну, как-то мотивировать, да, сказать, что это такое естественное, что ли, правило. Ну и вот такой пример, да, если натуральное число простое и больше, чем 2, то оно нечетное. Окей. Ну и подставляем на место вот этого числа, собственно, 2. И тогда мы имеем, что если 2 это число простое и больше, чем 2, тогда 2 нечетное. Так? Ну, то, что оно простое, это правда, но то, что 2 больше, чем 2, это неправда, это ложно. Ну, то есть мы на самом деле здесь, я бы сказал, что все-таки это в первую очередь иллюстрирует как раз вот нашу таблицу истинности для импликации. Да? То есть если мы вот это if-then формализуем как импликацию, как мы это и делали, ну, то получаем вот антицидент ложный, потому что он представляет себе конъюнкцию, в которой один из конъюнктов именно вот этот ложен, да, ну, а вывод все равно останется правильным. Ну, давайте посмотрим, что они дальше. Ну, это понятно, да? А что вот они дальше говорят? In this conditional statement, то есть условное предложение, ну, то есть то предложение, которое как раз формализуется с помощью импликации, both the antecedent and succedent, слушайте, я и привык его называть consequent, но кто-то вот называет succedent просто как синоним, are false. Значит, смотрите, если... Да. Ага, да, конечно, здесь вот это, ну, консеквент тоже ложен, да, я уже что-то пропустил это. То есть 2, значит, если 2 простое и больше, чем 2, то 2 нечетное. Ну, конечно, это ложно, что 2 нечетное, и ложно, что 2 больше, чем 2. Так? То есть у нас как раз случай тогда, когда из лжи следует ложь. Окей. The fact that we are committed to saying that the statement is true. Ну да, а смотрите, а все-таки, ну вот если мы говорим, что это для всех натуральных чисел работает n, ну значит должно вроде работать для двойки, да? У нас тут не было специальной оговорки, что мы двойку тут как-то исключили. Вот мы сказали, для каждого натурального числа. Вот это работает, так? Значит, мы должны сказать, что вот это все истина. Ну, по крайней мере, если, еще раз я говорю, мы это анализируем как импликацию, ну, то вроде да, из лжи следует ложь, и это все истина вместе. The fact that we are committed to saying that the statement is true shows that we should be able to prove one way or another that the statement that 2 is odd follows from the false statement that 2 is greater than 2. The X falso neatly encapsulate this sort of inference. Ну да, ну вот как я сказал, да, ну видите, то есть тут, когда мы говорим просто про импликацию и про ее таблицу истинности, это еще на самом деле не про выводы. Чтобы вот из импликации сделать вывод, нам нужно там модус поненс применить, как я говорил, да. Ну вот, тем не менее, мы можем использовать, то есть фактически здесь вот о чем речь идет, что у нас есть импликация из вот этой первой части фразы во вторую, и первая ложная, и вторая ложная. Ну вот, как мы говорили, такого рода импликация всегда будет истина, но здесь нам нужно немножко на этот пример вот с другой точки зрения, что ли, посмотреть, да, а именно посмотреть на эту штуку как на вывод, и тогда получится, что ну вот мы имеем как бы ложь, что-то ложное, и оттуда следует все, что угодно. И этот вывод остается валидным. Notice that if we define not A to be A implies falsum, then the rule for negation, introduction, and elimination are nothing more than implication, introduction, and elimination respectively. Ну да, видите, вот такой есть действительно в этой интуиционистской логике трюк. Вот я вам интуиционистская, вот которая не классическая, это без закона исключенного третьего. Ну, наверное, тогда уже на следующей неделе мы подробнее об этом поговорим. Да, но действительно, если... То есть тут есть такой трюк, что можно вообще даже не использовать отрицание как какое-то, так сказать, отдельное понятие, как отдельную связку, а просто считать, что отрицание – это вот как раз такая штука, когда из высказывания, которое мы хотим отрицать, следует противоречие. We can think of non-A expressed colorfully by saying if A is true, then pigs have wings. Where pigs have wings is stands. Как-то они плохо проредактировали здесь. For falsum. Having introduced the symbols for false, it is only fair to introduce the symbols for true. In contrast to false, true has no elimination rule, only introduction rule. Put simply, true is true. No, let's. So you see, we have still again these two constants, as I already explained, falsum and verum, or truth. And then for falsum, we have only what? Elimination. Yeah, and that's is actually ex falso, right? So we'll eliminate contradiction just by inferring anything we want, some arbitrary A from this, and kind of complementary thing that we may introduce verum, truth, just with no assumption at all. So it just true is true. That's intuitively speaking. Okay. Yeah. I don't know if we need really exercises. I think we already, no, at least this thing we illustrated with exercises we made earlier, right? No, this thing, right, where we refuted hypothesis or negated, if you like, by deriving contradiction from this, right? And these things, of course, are more formal, if you like, right? They do not correspond to some significant steps of reasoning. However, they are logically significant. You see, they are maybe just too simple, too elementary to be considered normally as important. However, if you analyze these things logically, of course, they are very important, right? They are very elementary. And of course, this thing like X falso is very important, right? It's, how to say, it's important logical principle that, as I say, one may accept or not accept, or trying somehow to limit its applicability. But of course, it's a very important logical principle. Yeah, but this again is, say, kind of formal, but you see, it's it makes this kind of symmetry of harmony, as logicians say, with the elimination of falsum. So we eliminate falsum and introduce verum. That's how it works. Okay. So what we have now on, but I think we should make a a break and until the next week. So we should treat disjunction, and that's actually a bit more involved disjunction, as you see, because it involves this reasoning by cases again. And then, okay, that's rather, it's kind of double implication, equivalence, called equivalence if and only if it's implication which goes both ways, not from A to B, but both from A to B symmetrically and from B to A. So that's not particularly complicated, right? And then it's very important something we'll talk next time about. Well, basically, it's this RAA, it referred to reductio ad absurdum. It's something we came across when we worked with examples. And basically, it's about excluded middle and about that turning point which distinguishes between classical and intuitionistic logic. Okay. Yeah. No, please ask me questions if you have questions. Right. I promised to tell you a couple of things about this. About this talk, where some of you may want to attend. So now I just put in chat a new Zoom link and actually an abstract of this talk. Okay, I should somehow also probably include the name of the speaker. Yeah, and title of the talk, and they're here. Okay. Yeah. No, okay, we have still 10 minutes. I can show you. Couple of things about Georg Kreisel. No, it's not here. Here, org. Kreisel. Yeah, like this. Yeah, you can read just no. He was working on something was called Hilbert program. I already, I think, told you a couple of things about David Hilbert. Remember when I talked about Hilbert style formal system and Gensen style formal system, right? And Hilbert actually had this visionary project of say formalizing all mathematics and probably all reasoning. And then many philosophers and logicians and mathematicians somehow discussing and prove different results, and that's still going on. Okay, these works of David Hilbert actually was about exactly 100 years ago, so it's 1920s basically, 1920s, later 1930s, about that time. Okay, and one important Hilbert's idea that I think Lev Beklemishim is going to discuss after Kreisel was so-called finitism. So his idea was this, that suppose we have kind of informal reasoning, just an informal just refers in logicians language, refers to kind of normal mathematical proof, kind of proof we came across, like doubling a square, or whatever what we proved, that there is no largest prime number and so on, right? Then we didn't use formal logic, and mathematicians normally do not use formal logic, but Hilbert project was that let's somehow make all mathematicians use formal logic and formal languages, and then we can just take a bare syntax, just take these formulas that that express certain proofs, and then we can do certain things with these formulas and prove certain theorems about these formulas. And why it's called finitism, because formula may be very long and kind of barely readable, but it's finite, unlike say, normal mathematician objects a set of all natural numbers, right? There's no larger number, and if we want to reason about all natural numbers, that means that we reason about something infinite. Or even if we talking about, say, infinite straight line and things like this. And in mathematics, of course, they're everywhere. And of course, infinity, it's kind of suspicious from logical point of view, right? People may say, okay, you might get it wrong, and it just could be contradictory, your reasoning about infinity. And so Hilbert just tried to make this, you see the trick. So you're writing formulas which semantically are interpreted as, say, something infinite and blah, blah. But formulas themselves are finite. And that's how he wanted to make kind of foundation of mathematics. So I think that Kreisel also worked on this project, and that's what Lev Beklemyshev is going to discuss now. And actually, title of Kreisel paper is this. Okay, I'll give you also in chat. It's you see, it's old paper in 1960, given on Congress of Mathematicians. That's the same kind of Congress that was supposed to be held in St. Petersburg in this July, but was canceled for obvious reason. Okay, and you see, it's exactly, it discusses informal concepts of proof in mathematics and ordinal logic. I can explain you later. It's some even more specific sort of logic, but it's a kind of formal logic. So let's maybe take 5 minutes break, and unless you have some very urgent question, I may answer right now. Пожалуйста, есть какие-то срочные вопросы?
Нет, все хорошо.
Отлично. Ну ладно, давайте. В общем, смотрите, кто из вас смелый, приходите на семинар. Кстати, потом через неделю, ну, или даже если хотите, напишите раньше, как на какие-то вопросы я смогу ответить тоже вот по этому семинару. Ну, кстати, их что-то можно задать, там будет, наверное, в конце вопроса. Руку поднять. Только не хулиганьте. Да. Хорошо, хорошо. Все, тогда увидимся. Это начинается вот через 5 минут.
Спасибо большое.
Спасибо. До
Спасибо вам.
свидания.
Всего хорошего.